Dr. Chabel was an associate research professor at Johns Hopkins University, you see, and he served various renowned positions like principal professional staff, system engineers, innovation lead, and the member of the S&T committee and the member of the innovation steering group at Johns Hopkins University. And he also has numerous publications in intellectual property and received 12 achievement recognition awards. And he's also a pioneer in UAV technology, AI, and machine learning, and autonomy. And he has been the visionary for the optimized signal-to-information architecture for dynamic software-defined multi-model sensing and fusion and true edge processing. The title of today's talk is slightly different from what I got here. It was Oculii enables 600 times reduction in latency energy factor for visual edge applications by moving sensors from imaging to vision. Actually, I like this title better than that one. So let's welcome Dr. Chabel, the founder and CEO of Oculii.
This title is the marketing hat, so you get both. Hello, everyone. Thank you for joining us. I basically have spent most of my career developing smart autonomous systems, and computer vision or machine vision has consistently been the bottleneck. And I got so frustrated, and we ended up developing this technology that I believe is going to be a major shift in the world of computer vision and machine vision. Because we've been living in a world of imaging sensors, and our eyes, which give us really excellent vision, are not imaging sensors, right? Our eyes are more like vision sensors. They process the scene and they output relevant information. And that's what we are doing right now on silicon. I want to show you examples of my frustration in my previous life. So these are my students developing fully autonomous robots. Okay? I give my students requirements that the robot must do X, Y, and Z, and it can only cost a certain amount of money. That's the only requirement I give my students. And over the few years that I worked with my students on building robots, we probably developed about 200 of them, but none of them had vision technology on board. Okay? And I'll show you in a second why that's the problem. But that's the world we've been living in for a good bit. I'm going to show you simpler examples now. We've been trying to automate these simple tasks, and they're still not very smart because they don't really have vision technology on board. Okay? I'll show you another one. That's one of my favorite ones, especially here in Korea. This is my first visit, by the way. I didn't realize it gets so cold. You're wasting a lot of energy with your sliding doors. They're not very smart yet. So these are simple problems that we can solve today with TinyML-like solutions if you have vision technology instead of imaging technology. I apologize, this is an audio-based video, but the bottom line is your smartphones are not really smart because they don't have any visual intelligence on there. Right? You can ask your phone to check the weather, to call somebody. Try asking your phone to do anything involving visual intelligence, and you're not going to get anything useful. So not only on the simple cases, but even on the more challenging autonomous cases, they're not going to get there unless they move from imaging to vision technology. That's been my philosophy for years, and I think time will tell if I'm right or wrong. And again, this is the fundamental problem that we have today. We've had for decades. We took camera technology or imaging sensor technology that was developed for human perception and human usage. You and I look at an image, look at a video, and process it very efficiently. But take that amount of data that a camera outputs and feed it into a computer, and it doesn't matter how good your computer or your processing is, it's a lot of data and you're going to struggle. So we end up always with solutions that are either too slow or too much energy or too expensive. And we realized that really years ago in my research, and we also realized that the fundamental way is to move from imaging to vision, starting at the pixel level. That's the shift that we as Oculii are bringing to the market. Our sensor is called Sensing and Processing Unit. It's basically a CMOS chip that you put a lens on there, and it has enough intelligence on board, starting at the pixel, to program it to output relevant information, like in the case when you're trying to detect a person is there. You can do that now very efficiently both in time and in energy and cost, using our technology. So again, we're moving away from imaging to vision. That's the bottom line. That's the architecture that we've developed. We have taken the pixel again from being only the sensor that collects photons and outputs of electrons to now collecting photons and outputting information. So when you talk about computer vision and machine vision, the pixel is the true edge. It's not near the sensor, it's not behind the sensor. The true edge in image processing is actually the pixel itself. And that's where our smarts start. So to give you simple examples here, and I'll try to go faster. Again, the example of detecting a person, the world now processes video on the left, and that's lots and lots of data. Our SPU processes all of that without creating ever an image and outputs the signal on the right. And that signal is plenty good. It's a low bandwidth signal, but it's enough to recognize there are two people in the room in that space and what they're doing. Same thing if you're doing gesture control. These are examples of use cases that we believe are ideal for TinyML using our technology that are not possible with imaging sensors. Instead of processing a video, you can do an ROI, that's the middle output, as well as the actionable signal that I showed you on. So not only are we saving energy, we're certainly a lot faster, and we can ultimately improve accuracy. Another interesting result I want to share here with this community, I'm sure many of you are familiar with hardware that has a CPU, a GPU, and a DSP. So we ran the face detection model on that type of hardware. And just to be clear, we did not run the model using all three. We ran the model individually on each one of those hardwares. And as you can see, the CPU doesn't do very well when you are providing a full image data because it doesn't manage, it's not very efficient at that task. That's why GPUs and DSPs have become popular. But notice when we reduce the amount of data that goes into that hardware, now the CPU is pretty much on par with DSP and GPU. That's a big deal in machine vision and computer vision, right? GPUs gain their fame because of image processing requirements, and now by moving the sensor from being an imager to being a vision sensor, you can go back to good old x86s and still do well. So not just in the energy I showed you earlier, even the inference, right? The inference and energy are highly correlated. But again, you can see here, by reducing the input size, you're able to get similar performances now on the CPU versus the others. And again, that would be a big, and I think for a community like TinyML, that would be a welcome output. So eye tracking is another use case that we are, that we are asked to compare with. And again, we're showing you kind of an example of how we can track the eye very efficiently. And then this is for hand tracking. So people tracking, face tracking, eye tracking, hand tracking. These are all use cases that are very relevant for devices to become smart, because we as humans actually process that the most. In our day-to-day interactions, that's pretty much the dominant aspect of our visual intelligence. So adding that level of visual intelligence to devices and places is a big deal. Again, as I mentioned to you on the accuracy side, because we don't scale the image down to low resolution, our accuracy doesn't suffer like alternative approaches do. This is a smartphone application for deblurring. I'm not sure I have much time to talk over that one. And then this is slow motion. Again, we're really showing the world capabilities that today you don't have because they are too expensive, too slow, or too much energy. And we're going to enable a class of those examples. Here we demonstrated high speed depth. I believe that demo was running at 700 hertz. And this might be a little bit more than a TinyML resource can do. But again, we're trying to kind of get you to realize that we have eliminated really the bottleneck that has always existed in the world of computer vision and machine vision when it comes to latency and energy and what have you. This is one of my favorite examples where a customer was asked us to whether we can actually do anything for flash floods. And we ended up doing this demo where what you're seeing on the left is actually raindrops. So we are tracking raindrops and counting them on the SPU and providing an estimate of the rainfall. So it turns out that's actually pretty accurate, and we were happily surprised by that little demo. And again, that's another TinyML application that you can't do today with imaging sensors, but you can do with a vision sensor like ours. I'm going to end on this. Just again, I want to leave you with the main data point here is that by moving enough smarts onto the sensor itself, starting at the pixel, we have eliminated the significant bottlenecks. In this demo we did years ago, by the way, that's long before Oculii was started, we captured a bullet in flight using our prototype. So think about that. You know, to do computer vision and high speed today, the amount of resources that you need. Tomorrow your cell phone will have this capability if the SPU is on there. And that's, again, and we're doing that in milliwatts. So that is a significant, because in this case the sensor is not outputting video, is not outputting images, it's actually processing at the pixel level in parallel and outputting the relevant information. In this case, it's the gunshot. What we have today is an evaluation board with the prototype. We call it the S11. We've developed a software infrastructure, and so, you know, for users who are interested, they can be up and running quickly. We don't have a lot of those left at this point, so we have a lot of demand. But I am a big fan of TinyML community, and that's why I'm here and presenting and sharing this with you. So if you're interested in this up and coming, really what I call a revolution in computer or machine vision, we're happy to talk to you about it. And we're trying to get this in high volume in about a year from now. So hopefully the next time I come to Korea, I'll have more samples, maybe free samples as well. So we're all about really low power, low latency, and low cost visual intelligence at the for edge applications. And one thing I completely did not mention at all is privacy, because we no longer output an image or video. We don't need to anymore. You can actually have our sensor on products, in your houses, in your offices, in your vehicles, and not have to worry about your personal privacy at this point. Thank you very much. I'm happy to take questions.